So in the game of roulette, a wheel consists of 38 slots numbered 0, 0, 0, and 1 through 36. Odd number slots are red. So there are 18 of them and are red. Even number slots. $18 of them and they are black. The two other numbers 0 and 0, 0 are in green, which would give the total count to be 18 plus 18 plus 2, which is 38. So we want to find the probability that the metal ball lands on green, must be and. So what is the probability that the metal ball lands on green and red? So probability of ball there is only one ball that's going to be spun around the wheel. So that ball is either going to land on the green slot or it's going to land on the red slot, but it can't land on both of them. So the probability would be 0. The next part we've already done in one of the previous videos. I picked the example only for part A, that where I changed or to and. So the next one, part B, is based on addition rule, and it is in one of our previous videos. So this is a problem on life expectancy. So the probability that a randomly selected 40-year-old male will live for 41 years old is 0.99757, according to the National Vital Statistics Report. So I don't want to write the entire statement over and over again. So what I'm going to do so PR stands for probability, and X is the randomly selected 40-year-old male will live to be 41 years, is the event. And I'll call that probability as simply P. So X would simply mean the 40-year-old male will live to be 41 years. So probability of X is little p or lowercase p. We have 0.99757. So part A would want to know the probability that two randomly selected 40-year-old males will live to be 41 years old. So we want to find the probability that the first person, I'll call X1, and the second person, both of them live to be 41 years old. So first person is X1, second person is X2. Note that both of them are independent of each other, and we can recognize that by looking at the phrase randomly selected. If two people are randomly selected, that the chances that they are related in some way is very, very small. So they are independent. So that would mean probability that the first male, first 40-year-old male will live to be 41 years, multiplied by the probability that the second 40-year-old male will live to be 41 years old. But the probabilities are the same for any 40-year-old male. And that's what we have here from the question. So it would be 0.99757 times 0.99757. Oh. Oh. So we could plug this in the calculator. So 0.99757 times 0.99757, which would give us 0.99515. We can typically stop at 2 decimal places. Four decimal places. You don't have to go up to 5 or 6 decimal places. So I can round it to 0.9952. Now, extending the idea, what is the probability that 5 randomly selected 40-year-old males will live to be 41 years old? So I'm going to index them the way I did it in the previous problem. The first one would live to be 41 years old, and the second one, and the third one, and the fourth, and the fifth. All of them, all 40-year-old males will live to be 41 years old. So since they're all independent, we could do the same thing that we did in the previous problem. So the first one does, the second one does, and the third one, and the fourth one, and the fifth one. So we have 0.99757 multiplied to itself 5 times. So that would be 0.99757 raised 5. So probability would be 0.9871. I'm rounding it to 4 decimal places. Part C, what is the probability that at least one of the 5 randomly selected 40-year-old males will not live to be 41 years old? So you've got to pay attention here carefully, because the probability that's given to us is the probability that the 40-year-old male will live to 41 years. So if that is the case, so that's what we have. But the question wants to know the probability that at least one of 5 randomly selected 40-year-old males will not live to be 41 years old. So whatever we are looking for is the complement of what we have. So using the complementary rule, we would have 1 minus 9,757, 0.99757. that would give us 0.00243. Now that is the probability of focus. The question now would want to know probability that at least one of the 5 randomly selected 40-year-old males will not live to be 41 years old. So probability of at least 1 is equal to 1 minus the probability of none from last time. So at least one 40-year-old male will not live to 41 years old is equal to 1 minus the probability that none of the 40-year-old males will not live to 41 years old. So semantically, if none of them will not live or none of them are expected to live up to 41 years old, it's the same as saying all of them live to 41 years old. So you can see the translation as to how I went from probability that none of the 40-year-old males will not live to 41 years old simply means all of them aged up to 41. So logically, that probability, all of them living up to 41 years old, is nothing but the probability that we found in part B. So that is 1 minus 0.9871. That would give us 0.0129. Part C also asks, would it be unusual if at least one of the 5 randomly selected 40-year-old males did not live to be 41 years old? Now, it is a very small probability. We found the probability that at least one 40-year-old male will not live to 41 years old is about 1.29%. And that is a small probability. I would consider it to be unusual, but I won't consider it to be a rare event. Could it happen? Yes, but with a very small probability. So driving under the influence, which we shouldn't do, among 21 to 25-year-olds, 29% say they have driven while under the influence of alcohol. Suppose we select 3 21 to 25-year-olds at random. So the keywords are, we are selecting 3 of them, and they're all random. So I'll call XK to be the kth 21 to 25 year old. So who has driven while under the influence. So according to the problem, it doesn't matter what K is, any 21 to 25-year-old, if picked at random, convey that they have driven while the probability that they have driven while under the influence of alcohol would be 29%. So the probability of XK for any person is P, I'll call it 0.29, which is nothing but 29%. Now we have selected 3 people, so 3 random people. Which would mean x1, x2, and x3. Part A would like to know the probability that all 3 have driven while under the influence of alcohol. So the first one has, because the way I defined xk is that the kth 21 to 25-year-old who has driven while under the influence of alcohol. So the first one has, and the second one has, and the third one has admitted to have driven while under the influence of alcohol. All 3 of them are random, so I can split them up and write it as probability of x1 times probability of x2 times probability of x3. Regardless of the individual, that probability is the same. So 0.29 times 0.29 times 0.29, which would give us 0.29 cubed. Okay. Cool. And that would give us a probability of 0.2439 or 0.02439. I can write that as 0.0244. It's about 2.44%. So same logic as the previous problem. So the probability that at least one has not driven under the influence is equal to the probability of 1 minus none of them have driven under the influence. None of them have not driven under the influence, which is simply saying probability that all of them have driven under the influence which is what we had in the previous part. So 1 minus 0.29 raised 3. .9756. Part C, what is the probability that none of the 3 has driven while under the influence of alcohol? So in part A, we wanted to know the first one has driven under the influence, second one has driven under the influence, third one has driven under the influence. Here, the first one has not driven under the influence. So driving under the influence is the complement of not driving under the influence. So I'm going to put it as complement with a C. Same with the second person and the third person. They're all independent. So that part does not change, but what changes is the probability, because if the probability that they drove under the influence is 0.29, the probability that they did not drive under the probability that they did not drive while under the influence would be 1 minus the probability that they did. They are complements of each other. So I can write it as 1 minus 0.29, which would give us 0.71. So here, since we know the complementary probability to be 0.71, we can simply multiply the probabilities 0.71 times 0.71 times 0.71, which would give us 0.71 cubed, so 0.3579. So there is a 35.79% chance that if I picked 3 21 to 25-year-olds at random, none of them would have driven under the influence of alcohol. Part D wants to know the probability that at least one has driven while under the influence of alcohol. Which is equal to 1 minus the probability none of them have driven while under the influence of alcohol. In other words, the first one did not, the second one did not, and the third one did not. So that is the probability that we found in the previous part. So 1 minus the probability that we found in the previous part is 0.6421, or there is a 64.21% chance at least one has driven while under the influence of alcohol. Keep in mind that there is a difference between one, exactly one, and at least one. And there is also a difference when we look at the probability of 3 people as a group and 10 people. The probabilities will not be the same because it's relative to the number of people in the group. Recording here. So according to a Gallup poll, about 17% of adult Americans bet on professional sports. Census data indicates that 48.4% of adult population in the United States is male. Assuming that betting is independent of gender, compute the probability that an American adult selected at random is male and bets on professional sports. So I'm going to define A to be the event that an adult is male, B to be the event that the adult bets on professional sports. So part A would want to know the probability that a randomly selected adult is male, so event A, and bets on professional sports, and would mean intersection. So A and B. So here the key word to pay attention to is independent. It states that assuming that betting is independent of gender. So based on what I wrote, events A and B are independent. And what do we know about independent events? If events are independent, I could write probability of A and B as simply the probability of A multiplied by the probability of B. So probability of A is 0.17. Sorry, it's actually 0.484. From the census data that we have, and probability of B is 0.17. So we just have to multiply them together, and we are able to do this because the events are independent of each other. And that gives us a probability of 0.08228. Now, using the result in part A, we want to compute the probability that an American adult selected at random is male or bets on professional sports. The conjunction here is or. That is an indicator that we have to use addition rule. So probability that the event is that the adult is male, or so union, the adult bets on professional sports. What does the addition rule state? It states probability of A union B is equal to the probability of A plus the probability of B minus the probability of A and B. So probability of A, we know that is 0.484. Probability of B is 0.17. Probability that an adult is male and bets on professional sports is not 0. If it is 0, then they can't happen at the same time. But it's not true that a male can also not bet on professional sports at the same time. And we know that probability from the previous part, which happens to be 0.08228. So we can plug that in here. So 0.484 plus 0.17 minus 0.08228. That gives us a probability of 0.57172. And that is using the addition rule in conjunction with the multiplication. So part C, the Gallup poll data indicated that 10.6% of adults in the United States are males and bet on professional sports. What does indicate about the assumption in part A? So part A, the probability was 0.08228. So now they're saying, well, according to the poll, probability of A and B turns out to be 0.106. So with this new data, we can say that probability of A and B is not equal to what we computed in part A, which is probability of A times probability of B. That would simply imply that our assumption of independence is incorrect. If, for instance, the new Gallup poll data indicated 8.228% of adults in the United States are males and bet on professional sports, then we can say that the assumption was true because the answer from part A matches the answer from part C. So our assumption is correct. but that is not true here. They don't match. So the assumption of independence is actually incorrect. So part D, how the information in part C affect the probability we computed in part B. So if you notice, that was the probability that we computed from part A. That's about 8%. If that increases to 10.6%, it is going to decrease the probability that we found in part B. So probability of A union B is 0.84 plus 0.17, but only this time it is not what we had, rather it is 0.106. The answer that we get is 0.548, sorry. It has to go down. So the probability went down slightly. It decreased by 3%.